Okay, hopefully you got the answers for the problems from last night, and hopefully it made sense for the most part. Maybe I'm guessing you got confused on the inverse sine problem, but other than that, it should have been pretty straightforward. Oh, and maybe the natural log one too, but hopefully you got them figured out. In this one, we're just going to do some more problems with the mean value theorem. Not going to be a lot of notes. Because most of this stuff is all just proving things, and I'm just going to tell you what it proves. We're not going to go through the proofs or why it works, because it's pretty simple. Like, the first thing it basically says, if you know the derivative of a function is greater than 0, then the function is increasing. And that's basically like we did when we were finding extreme values, and we'd set up a number line and we'd check the sign of the slope. We're like, oh, it's positive when we draw the little line. We were already doing that. We're saying, oh, if it's got a positive slope, it must be increasing. It's going up from left to right. Oh, if it's got a negative slope, it must be decreasing. Alright, that's all that says. This just proves it, and we're not going to prove it. We're just going to accept it. If anyone doesn't accept it, you can come in after school and I'll prove it to you, and it'll be fun. So that's one thing, and you're going to use that in your homework problems tonight. And I think that's the only new thing. The rest is just mean value theorem, using what we talked about yesterday, and just doing some different types of problems. So I'll just do a few examples of those types of problems and the way that they're going to be asked, just so you can see it, and then you can try them. The first one, this isn't really a problem. It's actually example 4 in your book. It just says if a car accelerating from 0, you don't have to write this down. This is just think. You'll have to think about this on one of your problems. I'm not going to tell you how to do it, but it just says a car is accelerating from 0, and it takes 8 seconds to go 352 feet. So if you know a car goes 8 seconds and 352, or takes 8 seconds to go 352 feet, you could say that its average velocity, 352 divided by 8, is 44 feet per second. Well, that's average velocity. Mean value theorem then would tell us that at some point during those 8 seconds, the car must have traveled exactly 44 feet per second. The reason that works is, think about it graphically. If this was time, this was feet, the car, takes off, hadn't moved, starts driving, maybe he just goes, something happens. And then here's 8 seconds, right? And he goes 352 feet. So when you do this, 352 divided by 8, you're just doing the average, the rise of 352 divided by the run of 8. That's like the pink line. Right? That's the secant line. That's just your average. Mean value theorem would tell us that at some point during those 8 seconds, we must have had a tangent line that was parallel. So if your average speed was 44 feet per second for the whole trip, at some point during that trip, you must have gone exactly 44 feet per second. It had to happen. There's no way you could have stayed under or above it the whole time. You had to have gone exactly that at some point. So think about that on the trucker problem. Next, let's see. Okay, I think I accidentally hit the record button with my hand. I don't think I missed much. Just gave the function, and I was looking at the interval. That's right. What was I doing? I think it's -1 to 1. Yeah, I'm just going to go with that. Which makes sense, because that's the domain of that. So we're looking at this function over this interval. The directions tell us that's from A to B. It says A is A, comma, f of A, and B That's all it's saying. Capital A and capital B are just the points on the graph out here. So find the equation of the secant line. Remember, secant line just means a line through 2 points. So if we want the equation of a line through, it's just the equation of the line through those 2 points. Right, there's 1 point. So your point A would be -1, comma, whatever. Plug it in, -1 squared is 1, 1 minus 1 is 0. Point B would be, plug it in, 1, oh hey, it's 1, 0. So the equation of the secant line, let's see, I get the slope, rise. So change in y over change in x. The slope is 0. Well, if you have something with a slope of 0, that tells you it's horizontal, right? Well, it wants the equation, though, of the secant line. So we know the slope. We could put it in point slope form, but that doesn't make sense. Why don't we just write the equation? A horizontal line, it goes through the y values of 0, right? If this is x and y, it's just going to be the x-axis. So y equals 0 would be our equation of the secant line. That probably won't, or that shouldn't happen on number 9, which you're doing. Oh crap, it might though. So it's just y equals that because we have a slope of 0. Where should I be? 10. So then the tangent line to f on the interval AB that is parallel to AB, right? I just read that. The tangent line on our interval that's parallel to that. Well, we just found that line. So now remember, we take the derivative of our function. So this is like the whole, this thing, blah, 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 blah. Yeah, that whole thing. We just found this side, right? That's just the slope of our secant line. So that's 0. So now we got to do, when does the derivative of our function equal that slope? So it's just the same as yesterday. So we got to do the derivative of that. 1 minus x squared to the 1/2. So it would be 1/2 times 1 minus x squared to the negative 1/2. That's the outside. Times the derivative of the inside would be negative 2x. So I'm going to drop that down to the bottom. 1 minus x squared. Might as well just put the square root instead of 1/2 power. I would have 1 over 2, but I got a 2 here. So half minus negative 2 is negative 1, so it's just negative x over that. So there's my derivative, negative x over the square root of 1 minus x squared. Oh, I could plug in c's. Notice I don't really ever do that. But that means if you know what value goes in here that makes this equal to 0. Multiply that by the bottom, so negative x equals 0. And, x equals 0, or c equals 0. So that's the point. But it wants the tangent line, so this happens at x equals 0. The slope is 0. This one's not too exciting. Good old classic bad example. I figured it would be good because I pulled it right out of the book. So this happens at x equals 0 and the slope is 0. All we have to do is figure out the y value when x equals 0. So 0 comma what? Don't plug that into your slope equation. We know the slope equals 0 when x is 0. We want to know the value of y when x is 0, right? We just figured out when x is 0, the slope of my tangent line will be 0, so what is the value of y? How high or up do I need to go? Go back to the original, plug in 0 for x. So you get the square root of 1. So at 0, 1, my slope is 0. So that'll be right there. So my equation of my line that's parallel to this line, this one was y equals 0, this one is y equals 1. I feel like I'm going too fast again today. Oh well. That was the same as yesterday. It's like, if you know the secant line and you know the slope of it, figure out where the slope of this one is the same. We did that. Then find the equation of that one. Well, since it was horizontal, I just needed the y value, so I plugged it in. That's all. The next ones you're going to have to do are great because it's like a 5.1 review. You're going to get a function, so I'll do this one. X to the third minus 27x. And it's going to say use analytic methods, so not your calculator, to find the local extrema. Hey, that was your quiz. So now that's just like, okay, you got to do that and find where the function is increasing and decreasing. So if you can do A, B, and C are really easy, because all we need to know to figure out where the function is increasing or decreasing is where the slope is positive or negative. But we're already going to do that to figure out part A. So it's just writing more stuff for our answer pretty much. So we need, it says local extrema, where, and then it's got B and C, but I'm just going to write it as B, intervals where the function is increasing or decreasing. We could have just wrote it as one thing, but they wrote it as B for increasing and C for decreasing, whatever. Here we go. We know we got to do our derivative first. 3x squared minus 27. And then remember where local extrema happen, where the derivative equals 0, where the derivative does not exist, or endpoints. Do some counting. There's like 3 things we need to check. Doesn't look like we're going to have to worry about endpoints. There were none given, and the domain of the original, the key to look at the original, is whole real numbers. I mentioned one time at the whiteboard that in the domain of, or when we did like the derivative, when we looked at the domain, that would help guide you to the domain of the original. And I think by looking at your quizzes, some of you thought that that's all you would look at. So I think there was some confusion there, but yeah. The domain of the original is all real numbers, so we have no endpoints. So what we care about is where the derivative is 0. So 3x squared minus 27 equals 0. Add 27. By 3, square root it, so I get plus or minus 3. Well, so now when we set up our thing here, negative 3, 3, check our slopes. So remember, you're checking slope on this. Don't plug it into the original here. You're checking slope. You're not checking what the y values are. So if I'm checking slope, negative 4 squared is 16. 3 is 48, minus 27 is positive. 0 minus 27 is negative. And then a million squared is huge. Subtracting 27 isn't going to affect that, so that's positive over there. Okay. So we got positive, negative, positive. Which tells us we got our local max at negative 3 something. Local min at 3 something. Should just plug those in now. Now we're trying to find y values, so now we use the original. We're not looking for slopes. We're looking for the y values on the graph. Negative 3 to the third is, what is that? Negative 27. I don't want to do this. Plus 60, plus 81. Negative 27 plus 81. 64, I think. I don't know. This could be wrong. I don't care. 3 to the third, 27 minus 81. 27 minus 81, negative 64. Who cares? So there's your local max and min. That's just like you did before. Now B is easy. If you've done all this and you've got this little picture. It says intervals where the function is increasing and decreasing. All you do is look at your little picture. If you've got it, you're done. So it's increasing here and here, wherever the slope is positive, right? We're not going to prove that, but like I said, we can. So all you have to write is the intervals that it's increasing. This thing goes to the left forever. There should be arrows. So it's increasing from negative infinity to -3. And it's decreasing from -3 to 3. Oh, and then another place where it's increasing, if you write it in interval notation, you write it like this. It's also increasing from 3 to infinity. So from negative infinity to -3 is increasing, and from 3 to infinity is increasing, and decreasing in the middle. Alright? So that's it. It's just like 5.1, but 2 extra questions. And then by 5.3, we'll have like 3 or 4 other things we're going to answer using these same ideas. So like I said, you're going to get lots of practice at doing this and figure out a way to make you better at it than your quizzes were. I think that's all I got to say about this. Hopefully, I don't know if I made much sense. I suppose you want some problems to do. Oh, there they are. These quick reviews are just for fun. Number 9 is the one about do the equation of the secant line and the equation of the tangent line. And then these 4 are basically just doing local extrema again. Oh no, 11's not. Oops, so it's just these 3. These 3 are doing the local extrema and where it's increasing or decreasing. So hopefully you find success on those, and I will check those tomorrow. Wow, you got like a long time to do this, so you better be done.